Welcome to This Explainer. Today, we're diving straight into an urgent environmental investigation currently underway on Belize's stunning Placencia Peninsula. We're looking at a comprehensive suite of technical reports, backed by some seriously extensive field data, to unpack a quiet crisis unfolding along this highly developed coastline. It's essentially a story of natural coastal dynamics colliding head-on with rapid human development. But more importantly, we're going to explore the highly engineered, science-based path forward that researchers have mapped out to save it. Right off the bat, let's look at this alarming revelation straight out of the project's executive summary. This quote perfectly highlights how desperate individualized attempts to stop coastal erosion are, well, actually making the whole crisis worse. See, when property owners build these unstandardized rock walls to protect their own land, they totally disrupt the natural flow of sand. So what's intended as a shield quickly becomes a weapon against the shoreline itself, fundamentally altering the coastal system and triggering failures that just cascade down the beach. Section 1, a coastline in crisis. Now, to understand the scale of the threat, we have to look at the geography. This isn't just one unbroken stretch of sand. Researchers divided our study area into 4 distinct embayment segments, working south to north from Placencia Village right up to the Riversdale headland. And the findings we're looking at today? They rely on a massive data set of 126 different beach profiles and nearshore bathymetry collected across these very specific zones. The entire peninsula stretches just 24 kilometers. That's it. Yet, despite this relatively small footprint, an astonishing 72% of its length is already developed. We're talking about dense beachfront residential and commercial properties, all facing an immediate risk from an eroding shoreline. And here is the crucial point. This coastline has virtually no natural height advantage. According to the Coastal Zone Status Report, dry beach elevations here sit at a dangerously low 0.5 to 0.7 meters above mean sea level. That makes the peninsula incredibly vulnerable to even minor increases in wave action, longshore currents, or tropical storms. When a coastline is this exceptionally low and this heavily developed, there is absolutely zero margin for error. Section 2. The problem with armouring. Let's look at the visual evidence of what happens when communities rely on a false solution. These stark drone images offer undeniable proof of how unstandardized rock walls absolutely disrupt the shoreline. You can clearly see the jagged borders. Instead of a smooth beach that allows sand to flow naturally with the currents, we're left with a fractured system. These rocks and seawalls physically block natural sand movement, trapping sediment in some areas while completely starving others. The Coastal Zone Status Report provides the hard data here, showing that this piecemeal approach to armouring is actually a primary driver of localized beach starvation, because 71% of the developed coast relies on this chaotic mix of rocks, seawalls, and wood or vinyl pilings. The natural longshore transport of sand is fundamentally broken. Think about it. When one property armors its shoreline, the wave energy gets deflected, which then causes severe, accelerated erosion to the adjacent, unprotected properties downdrift. It's a vicious, self-defeating cycle. Section 3. The science of sand. So, if rock walls are failing, what's the true science-backed solution? The design report points to something called beach nourishment as the definitive answer. Now, this isn't just about casually dumping sand on a beach. It's a highly precise engineering method designed to duplicate the natural beach profile and extend it seaward. By shifting away from hard concrete and rock, nourishment restores those dynamic, natural coastal processes, providing a natural buffer that absorbs wave energy rather than just deflecting it. You can see the mechanics in action right here. A proper nourishment project involves actively dredging compatible, high-quality sand from a carefully identified nearshore borrow site, sometimes an inlet channel, and then literally pumping it through large pipes directly onto the shoreline to rebuild that critical protective barrier. The engineering behind this is fascinating and incredibly systematic. First, sand is dredged and pumped to build up the specific berm and dune heights needed to prevent storm overtopping. But the absolute cleverest part of the design is step 3, constructing a steep 1 to 5 foreshore slope. By building it steep initially, engineers drastically minimize the amount of construction equipment operating directly in the water. Over time, they simply allow the natural wave action to equilibrate and smooth out that new slope. They're basically letting nature naturally reshape and settle the beach. Now, who knew sand could be so demanding? What's really interesting is that the success of this entire multi-million-dollar project hinges on a microscopic measurement, exactly a 0.43 millimeter median grain size. The researchers actually took 40 sediment cores and over 160 surface samples to ensure they could match the native sand perfectly. Using this specific, relatively coarse sand is crucial because it limits the amount of dry beach lost during that natural equilibration process we just talked about. Section 4, 4 sites for recovery. Let's transition from the raw science to the actual blueprints. These technical cross-sections map out the physical transformation. The blue lines show the steep, eroded current state, while the orange lines plot exactly how the new beach fill will advance seaward. In these designs, the back beach elevation is uniformly raised to 0.6 meters above sea level, providing that desperately needed buffer against the ocean. And here is the ultimate goal brilliantly illustrated. The red line marks the proposed post-nourishment shoreline. Notice how far out it sits from the current water's edge. This new sand will physically bury those failing rock walls, essentially hitting the reset button on the entire coastal dynamic. If we look at a specific impact zone, the apex of the bay at Placencia village, we can see the real-world impact. Right now, it's suffering from a starving beach width, where longshore sand transport is entirely blocked. But post-nourishment, the shoreline advances 20 to 25 meters seaward. So the beach width won't just be maintained, it will be effectively doubled. And because this specific area has a high rate of sand transport, this newly widened beach will act as a feeder, continually supplying sand to the beaches further south over time. Section 5. The cost of inaction. Why does it matter that we embrace this macro-level engineering immediately? Well, the stakes go far beyond just losing a place to put a beach towel. The data is undeniable here. The cost of inaction is not zero, and local families are already bearing the financial burden. We're talking millions in lost tourism revenue, canceled bookings, and direct infrastructure damage. When the beaches vanish, property values plunge, local employment takes a massive hit, and the public completely loses access to the shoreline. Plus, doing nothing just guarantees even higher, escalating costs for emergency, reactionary protection works down the line. We have the technical reports, we have the blueprints, and we even have the exact sand grain measurements required to fix this. It leaves us with a critical question about the future of our shorelines. Can coastal communities abandon panicked, fragmented individual defenses and unite behind a unified, science-based adaptation before the economic and environmental costs become too high to bear? Can we trust the data enough to adapt before time runs out? Thanks for joining me for this explainer. Keep questioning, keep learning, and I'll catch you in the next one.